to our repertoire, to our arsenal, so that we can solve more complicated problems involving multiple forces. And that's the concept of weight and mass. So this is 20.2.5, am I right? Okay. And it's not a very lengthy unit. The examples are very simple. And you're going to be getting assignment number 2 today, which deals with rivers and boats and that kind of thing, which will be due next Wednesday. So we have to step into the realm of science and not confuse weight with mass. I think most people, probably up to and including even junior high students, would say weight and mass are synonyms of the same idea. And the reason for that is the general world out there doesn't care about the difference between weight and mass. And there's a number of reasons why they don't. One of the things I'll tell you is weight is measured in newtons. So if you go and get your driver's license and they say, well, what's your weight? And you say 1,520 newtons, they're just going to look at you funny, right? Unless they have some kind of background in science or physics. So we're going to have to make sure we understand the difference between weight and mass, and then if you know the weight of an object on Earth, you can calculate its mass on Earth. And if you know the mass of an object on Earth, you can calculate its weight on Earth. But one of the things we will learn very shortly is that weight can change. And I'm not talking about bulking up or changing your diet. I'm talking about just going to a different place. Would you agree that when you step on a bathroom scale, it's showing your weight? It's telling you it in kilograms, but it is measuring a weight. If I glue my shoes to that bathroom scale and jump off of a diving board and read the weight when I'm falling, it will read 0. That's why I'm weightless when I'm falling. That's why when you go over the top of a curve or a path on a roller coaster, everything feels weightless. It's because you are weightless. Your weight is 0. I can also change my weight to going to the top of a mountain, where my weight will be less, because I'm further away from the center of the earth. A lot of world records were broken in, I want to say 1967, but I think that date might be wrong, when the Summer Olympics were held in Mexico City. Because the elevation of Mexico City is so high, a lot of records were broken because people weighed less. They could jump higher. We'll talk more about that when we get into forces of gravity. But in the meantime, let's get started here. Definitions. What mass is a measure of how much matter an object has. And this is a tricky thing. This is a really greasy thing to wrap your head around. The first thing is, when I say the amount of matter, I'm not talking about the amount of space, which is volume. If I look at the mass of my car and you made a car out of styrofoam, and you even painted it to look exactly like my car, I think it's obvious that the mass of that model is different than the mass of the car. So how is it we determine mass? And this might give you an idea of what mass really is about. Mass is measured using a balance scale. So when you stand on a bathroom scale, I know that it's telling you your mass in kilograms or pounds. But it really should be calibrated in newtons, because that is not a balanced scale. Would you agree that the amount of matter that I am made of wouldn't be different if all of a sudden I could be transported to the moon? It would be the same amount of matter. The amount of matter I have is not going to change when I go on top of a mountaintop, even though my weight is less. So why does a balance scale ensure that that's the case? Well, if I have this balance scale, so you understand what a balance scale is, right? And to be honest, nobody uses balance scales anymore. They're very rare. And the reason is we don't go to the moon very often. And we don't change our location by climbing up on mountains very often. Or if you are a mountain climber, you're not really concerned about your mass. That's not what you're talking about. You're talking about recreation at that point. So I have some objects we're going to put on the scale in order to determine the mass of something. So by placing an object with an unknown mass on one side, the scale would tip, right? So then what you do is you start putting masses that you know the values of on the other side until it balances. And whatever gravity is pulling down on the left side with will be the same as the force of gravity on the right. And I'm jumping ahead of a visual here, but if I do that, I put I put these kittens in here, it's going to tip, right? So then I walk over and I get all of these masses that are known to me. I have a kilogram mass, I have 500 grams, 250, 10, 50, 100. And I start putting them in, and I discover that things get balanced when I have 1 kilogram and 250 grams and 10 grams. What is that, 1,000, 1,250, 1,260 grams. I know that this is 1,260 grams. Let's not worry about how I know these masses. That's a different story. Would you agree the reason this is upset here is because there's more gravitational force acting on the kittens than the empty basket? Okay. So what's happening here is you have this force of gravity. It is a force of gravity. We're not measuring it. I'm just explaining that there's a force of gravity there that's not acting on the other side. But when we take those masses and we put it in the basket to balance things, we know that it will be balanced because if the masses are the same, there will be an equal force of gravity acting on there. Are you with me? So it's balanced. This is how we determine the mass of an object in principle. I've got forces of gravity written here, which is not mass, but it explains why this is balanced. Now, this is the Earth. I mean, I talked about the moon a while ago. I think it's kind of common knowledge that the force of gravity on objects on the moon is less than it is on Earth. And I'll tell you right now, it's about 1/6. So in an ideal world, if you can have a vertical jump off the ground, I'm not going to jump and embarrass myself, of this far, you'll be able to jump 6 times further on the moon. You want to be careful because you have inertia. And when you come down from a very large height, you're still going to hurt yourself. Okay? That's why if you watch people walking on the moon, they kind of shuffle along. They don't jump because you could get out of control. And last thing you want is to tear your spacesuit, I would suppose. So we go to the moon. Well, what happens? When you go to the moon, will this still be balanced? Yes, it will. This force of gravity is going to be quite small, but this force of gravity will be quite small as well. And the idea there is that it doesn't matter. We know that this is 1,260 grams. So whatever the force of gravity pulling on it, if it's balanced, is the force of gravity pulling on the kittens. Are you with me on the concept of a balance scale? Okay. Briefly, and I think I might have mentioned this, these masses are determined by a definition of what 1 kilogram is. Have I mentioned the fact that in Paris, in a vault, there's a 1 kilogram mass? I don't know when it was created, 100 years ago, maybe a little less than 100 years ago. And the scientific community got together and said, this is a kilogram, everybody. If you need a copy of it, we can make you a copy, but you can't keep the original. So industries have copies of a kilogram, and they use it to calibrate devices. So getting back to our discussion of mass and weight. What is weight? Weight is the force of gravity. So if I go back and look at this diagram, this force of gravity here is the weight of these masses. This force of gravity on the right is the weight of the kittens. And that brings up the idea then that mass is measured in grams or kilograms, but weight must be measured in newtons. It's a force. So it's the measure of the gravitational force pulling on an object towards the surface of whatever it's on. And weight is measured using a spring scale. And I ran out of time, so I didn't get a chance to, put together as many slides as I did for the kittens. All I got to was there's a spring scale. And you can't read it here. You maybe can kind of make it out. If I told you that says newtons, you can tell it says newtons. And it goes up to, I think, 1 newton. So this spring scale, and we will study spring forces in detail and do a lot of lab work with them. You understand that springs can be very hard to stretch, but some springs are easier to stretch. Well, this one doesn't take a lot of work to stretch at 1 Newton. And I've indicated here with a red line, because you probably can't see it otherwise, there's a little piece of metal that's sticking out. And it's at 0 right now. So the idea is, and maybe it's good I didn't animate this because I don't want to hang the kittens from this, but if I were to hang the kittens from that, it would stretch. And it would show us how many newtons of weight the kittens are. I'd put them in a basket first. I wouldn't like hook it in their collar or something. I'm not insane. You would put them in a basket, you'd hang it there, and then you would read how many newtons of force. Yeah. You would read how many newtons of force gravity is acting on them with by reading this. And it might be that you get, I'm going to say you get 13 newtons of force. Which would mean, I guess I'm telling you that this force of gravity is 13 newtons. It's probably closer to 12.5, but we'll get to that later. Okay? And I can see some of you trying to figure out why that's the case, but that's okay. We'll get to that. So I hang the kittens. I put the kittens in a basket, and I hang the basket from the spring scale, and it says 13 newtons. Leaving aside for a moment the fact that this doesn't go up to 13, it doesn't matter. If I go to the moon, what will it read? Will it still read 13 newtons? Well, no, because the reason this is stretching to the 13 Newton mark is gravity is pulling the basket of kittens down. But on the moon, gravity is 1/6 of what it would be on Earth. So if you take 13 divided by 6, 2.17, I think. Let's call it 2.2, just because we're just talking round numbers here. So when you take a look at this, here's Earth. What's the mass of the kittens? 1.26 kilograms. What's the weight of the kittens? 13 newtons. Go to the moon. What's the mass of the kittens? 1.26 kilograms. What's the weight? 2.2 newtons. The weight changed because the force of gravity is different depending on, the moon's not a planet, but I'm just going to say depending on the planet that you're on. So basically what you do is you take an object of unknown weight and you hang it from a spring scale. I used to say that nobody really has spring scales in the real world, but when you fish, you use them. If you've done any fishing, most likely you're carrying around a spring scale because it's very handy. I mean, do you want to carry around like a bathroom scale and flop the fish on there and it's, flopping all over? No, you just hang it from the spring scale. So we're going to just write out a summary here of everything we've learned about mass and weight. Mass is measured in kilograms. I'm not going to put in here the definition of these in words. I'm not going to write, oh, it's the amount of matter. It's kilograms. Weight is measured in newtons. Mass is measured using a balance scale. Weight is measured using a spring scale. Now, I guess I have to address this. Let's talk about our kittens. You have a basket of kittens, and it has a mass of 1,260 grams. And you're on Earth, and that happens to be about 13 newtons. You're with me? As you carry that basket of kittens around to show your friends, is the weight going to change? No, because you're on Earth. The weight can change if you go to a different planet or you change your elevation. So the fact of the matter is, the weight of objects on Earth is pretty much constant. Your weight doesn't change unless your diet changes or your exercise habits change or you're carrying stuff. You go around to different places, you fly overseas, your weight is the same. So for that reason, when you look at a spring scale in a grocery store, you've got those scales there that you can hang the stuff on, that's a spring scale. It's measuring weight, but it doesn't say newtons, does it? I think it's important you understand that it should say newtons, and somebody has scratched off the newtons, figuratively speaking, and put in the equivalent masses. Because on Earth, 1.26 kilograms of kittens is always going to be 13 newtons, 12.5, whatever. Okay. So we can use a spring scale and have it calibrated in grams. In fact, if you take a look at this, there's a gram side. But this, in measuring grams, would be useless if I took it to the moon. Right? So you will often see spring scales calibrated in grams or kilograms, but that's just because we're using them in the same gravitational field all the time. So it gets a little tricky. What else do we know? Well, mass remains constant. And you have to take that statement with, as they say, a grain of salt. You have to understand there's a subtle set of circumstances behind it, which is that I'm not talking about, can your mass change? Yes. Can the mass of the kittens change? Well, yes, it will. Because they're going to grow, right? They're going to eat, their bones will grow. I'm talking about when you move an object with a known mass to a different location, does its mass change? And it doesn't. It doesn't matter where in the universe you take, went the wrong way, this 500-gram piece of material, it's 500 grams. Whereas weight depends on the gravitational field. And I might as well amp this up a notch and just write something more technical, gravitational field, because we're going to have to talk about it sooner or later. The gravitational field determines the gravitational force. The Earth has a gravitational field. But the Earth's gravitational field has different strengths depending on where you are on the Earth. On a mountain, it's slightly less. Believe it or not, if you go to Calgary, the gravitational field is weaker, measurably weaker. If you do an experiment in Edmonton or Wetaskiwin to determine the gravitational field of the Earth, you will get a slightly higher value than you will get in Calgary or Banff. Very slightly higher, but it's measurable. And that, I think, is essentially covering it. Does anybody have any questions about the difference between mass and weight? Okay, so how do we calculate weight? Well, how do we calculate the weight of the mass of an object? Let's consider an object that's falling. So we're going to talk here about an object that's in free fall. I'm choosing an apple here. And there are no frictional forces, which for an apple is pretty much true unless you let the apple fall from a very tall building, then the friction builds up over time. But certainly dropping an apple from a height of 1 meter or so will create very little friction. In such a case, the only force acting on that apple is the force of gravity. And this right here that I'm going to highlight, everyone, is not something that is new today. We've written that a number of times, right? What's new is me telling you that that's called the weight of the object. So the force of gravity acting on that apple is its weight. Now, if I were to go back to the question we talked about where I said F net equals ma, remember that? So F net equals ma. And I told you that this is one way to describe the net force, and the other way to describe the net force is to look at the free body diagram. Well, what is the net force according to the free body diagram? It's the force of gravity. So listen very carefully though, in the case of a falling object, its weight is the mass times its acceleration. Would you agree if I held that apple in my hand, there's still weight, but it's not accelerating? We're just looking at how we can find the weight by imagining I let it go. So this is the weight. This is the force due to gravity acting on the object. Well, we know what the acceleration of a falling apple will be, don't we? It's 9.81 meters per second squared. And what that means is if you take the mass of an object times 9.81, you will get its weight. even if the apple is being held in your hand, that will still be the weight. So the force of gravity is the net force, which means you take, to find weight, the mass times the acceleration due to gravity, but we use this. We do not use A in our weight formula. There's a reason for that. Do I have a weight? Am I accelerating? No, so you can't calculate my weight by taking mass times my acceleration because you'll get 0. So when we see g, it's not acceleration of the object, it's the acceleration due to gravity. And you can nitpick on that and say, well, what's the difference? Huge difference. In fact, I would prefer to call this the acceleration due to gravity. I would prefer to call it what's called the gravitational field strength. And I would prefer to do that because then when I do teach you about gravitational fields, you'll go, oh yeah, he's used that terminology before. Oh, it's in your notes, isn't it? It's right there in bold. Sorry for implying that you had to write something down that you didn't have to write down. This quantity is also called the gravitational field strength. And I would never use vectors here. I would use absolute values. Okay. So it's 9.81 meters per second squared, or it's a real shame about this because they used to have a second set of units on your formula sheet for G, and I don't know why they removed them. Newtons per kilogram. Of course. It's newtons per kilogram because if the weight of an object is the mass times 9.81 newtons per kilogram, it's just telling you that for every kilogram, be careful, never mind. It's telling you that for every kilogram of mass, there's 9.81 newtons of weight. So if it were 2, it would be 19.62. This is why I said it was about 13 newtons for the kittens. I should have said maybe 12.5, but if you take, well, you can try it. What's 1.26 times 9.81? It'd be closer to 12, I'm guessing, than 13. 12.4. So 1,260 grams of kittens on Earth will pretty much have a weight of 12.4 newtons. That weight may change slightly when you climb mountains or go into valleys and stuff like that, but that's unimportant. All right, let's take a look at some very quick examples. But before we do, here's the formula as it appears on your formula sheet. I want to point something out to you, though. Would you agree that when I talk about Newton's second law, we pretty much always write that? I mean, with or without vectors, I don't care. Look at how it's written on your formula sheet. You may not have even noticed that. It's not written as F equals ma. It's written as A equals F over m. Same thing here. I will very rarely write this. I will write that. But again, these two things are different. This is talking about what's actually happening to an object. Is it accelerating or not? This is just talking about any object at any point in time. Let's do the examples now. Very quick examples. What will happen to your mass and weight when you go to the moon? Mass remains constant. Weight will decrease. It's a pretty trivial thing to find the gravitational field strength on the moon, given that I've already told you gravity is about 1/6 as strong on the moon as it is on Earth. So the gravitational field strength on the moon is about 1.6 meters per second squared, or newtons per kilogram. What is the weight of a 60-kilogram astronaut on Earth? Find the weight on a planet where the force of gravitational attraction is only 1/10 as great. Well, for A, I'm just curious, is yours formatted that way, or does it have A and then B? Yeah. Oh, okay. The force of gravity on Earth will be equal to, well, mg, which is equal to 60 kilograms times 9.81 newtons per kilogram. Whenever I use this formula, I use newtons per kilogram. Whenever I use F equals ma, F net equals ma, I use meters per second squared. I mentioned this before. You understand this is going to be pretty close to 600? Because 9.81 is almost 10? Okay. But we want a more precise value. 60 times 9.81 gives me 589 newtons. I am not interested today in significant figures, okay? We don't care about that. We're learning and I'm teaching right now. What will be the weight of an object if the gravitational attraction is 1/10 on this new planet? It will be 1/10 of this. And I don't think we really need a formula for that. You're just saying gravity is 1/10 as strong. So we're going to take this 589 and divide by 10 and get 59 or 58.9 newtons. Any questions with example 2? What is the weight of the same? Number 3, 5.5 kilogram backpack weighs 82 newtons on the surface of the moon. What is the calculated gravitational field strength? So here you go. You need to know, everybody, that this is G. And G is a vector. It has a direction. By the way, what is the direction of every weight? Down. Okay. I didn't talk about that, but it's always down. We're not worried about that. So F of gravity, which is weight, equals mg. We can put in the weight, 8.2 newtons. Put in the mass, 5.5 kilograms. Notice when you solve for G, you're going to get newtons per kilogram, which is meters per second squared. But the backpack may or may not be accelerating. And by the way, the backpack could be accelerating up because you're moving it up. Its weight will still be whatever this number is down. Is it going to be 1.6? 1.5 it works out to. That's why I kind of said, what is the calculated value? It should be 1.6, but it's working out to 1.5 here. A physics book has a mass of 2.2 kilograms. What is the weight on Earth? This is what I meant earlier when I said this is kind of a very basic lesson when it comes to the calculations. 2.2 kilograms times 9.81 meters per second squared. Let's round to the nearest Newton. And can you tell me, is it 21?
21.6.
It rounds to 22.
Yeah.
Okay. What is the weight on Mars? Well, 2.2 kilograms times. You'll notice here, for some reason, I've got 3.7 meters per second squared. I guess we have to understand that that is correct, but we need to think of it in terms of newtons per kilogram. I say 8.1? Yeah? 8.1 newtons. And number 5. Of all the planets in our solar system, Jupiter has the greatest gravitational field strength. By the way, we know these gravitational field strengths, not necessarily because they've been measured on the planets. There are ways to calculate them, based on the size of a planet and the mass of a planet. And we can determine the size of a planet by looking at the planet in a telescope and doing some basic trigonometry with similar triangles and find the size. And we can determine the mass, and we will learn this in the next unit, because we can track a planet around the sun, and if we know the distance, which is measurable, you can use Newton's universal law of gravitation to find the mass. That's why we know the mass of the sun. That's why we know the mass of the Earth, because of Newton. Anyway, it's very, very strong gravitational field. Well, not very, very strong. Strongest on Jupiter. A half-kilogram pair of running shoes weighs 11.55 newtons. How long would it take the running shoe to reach the surface of Jupiter if you dropped them or it from 3 meters? This is a kinematics question, right? VI is 0. D is 3. I'm going to not use vectors here. Everything's down. Let's just use positive for down. What else do we know? Oh, acceleration is 9.81, right? Okay, good. No, because it's not on Earth. Maybe it's 9.81, but we need to calculate that. So we're going to use our weight formula. Force of gravity equals 5 equals mass times g. So, I hope you understand this. You see this equation has 2 g's? I hope you appreciate the g on the left is just a label, and the g on the right is an actual thing. Okay. So this is 11.55 newtons equals the mass of 0.5 kilograms times g. So when you get g, you should be getting 23.1 newtons per kilogram by my count. Okay. Over twice the acceleration due to gravity on Earth. And you'll notice that what I do here is all of a sudden I write 23.1 meters per second squared. This weight is in reference to maybe just holding the running shoes. They're not accelerating. But if we let them go, this number becomes their acceleration. It's a straight kinematics formula. I guess we're going to use d equals a half at squared. So you'll have 3 equals 1/2 times 23.1 times t squared. Three times 2 to get rid of that half is 6, divided by 23.1 gives you this. Take the square root, half a second. 1 what? That long. Not 1/1000, like half a second. 3 meters, so I'm 2 meters tall. Well, I'm not, but 2 meters is a tall person. 3 meters is pretty much the height of the ceiling. So you're dropping an object from the ceiling and it's hitting the floor in less than a second.